So in the last class, we were looking at this problem of empirical risk minimization, right? Essentially, it's the classification, the binary classification problem, wherein you have some observable, such as an image, and you want to classify it into one of two different classes, right? For example, is a particular object present in that particular image or not, right? And we saw that if we knew the distribution from which these images and the joint distribution of the image as well as the class, then there is something optimal we can do with respect to the risk, right? And that would be to choose the conditional expectation, or in other words, just use the map estimator, correct? That minimizes the probability of misclassification. So this is sometimes called the base risk, the optimum base risk. So the minimum, so basically R of G star, this is called the minimum base risk. Right? But in practice, we do not have access to the joint distribution Px. At best, we have a bunch of samples drawn IID from this particular joint distribution. And the goal is still to perhaps try to perform as good as R of G star or something close to R of G star. But in any case, we want a handle on how good a particular estimator does, right? And one popular technique is to perform what is called empirical risk minimization. You compute this empirical risk and you try to find the G from a class of classifiers that minimizes this particular empirical risk, correct? And that is what is very commonly done today. There are different variants of empirical risk minimization. Sometimes you don't just minimize this particular risk, but at times you minimize the weighted sum of the risk plus some other function of G, right? So there are different optimization problems that one can frame, but today we want to understand how well empirical risk minimization performs. And is it possible to derive bounds on the performance of this empirical risk minimization algorithm, right? So firstly, the first question we tried to answer was so this empirical risk is trying to approximate the Bayesian risk, the expected risk of a particular classifier. So how close is the empirical risk to the expected risk? And since the empirical risk is basically a normalized sum of Bernoulli random variables, we can use our favorite Chernoff bound to derive, to just say that the probability that the empirical risk deviates from the expected risk by an amount delta is exponentially decaying in n and delta square, right? So we get that essentially for free. But this is for a given G, right? For a given classifier G, we have the following tail, right? But now what we want to know is how well our estimate or the classifier obtained from empirical risk minimization performs. And this is not a sum of IID random variables. And to see why that is the case, let's look at a toy example. Right, suppose that so we have some x1, y1 up to xn, yn, and let us say that our class of functions or the set of classifiers that we are allowed to choose from is sort of the trivial class. It declares everything as 0 or everything as 1. All right, so it consists of two functions, g1 and, or let me call it g1 and g minus 1, So g1 of x is basically equal to 1 for all x, and g minus 1 of x equals minus 1 for all x. Okay, it's not a particularly useful classifier, but just to illustrate the point, let us look at these two functions. Okay, and let's try to analyze the empirical risk. Okay, let's assume that the marginal p of y, probability that y equal to 1 equals some alpha, so that the probability that y equal to minus 1 is equal to 1 minus alpha. Right? This is only the marginal with respect to y, because after all, even our classifier is not really doing anything useful. It's not making use of the knowledge of x. So what does summation I equal to 1 to n indicator g of x not g of xi not equal to yi look like? Yeah, correct. It's binomial, agreed, but for a given g it's binomial with a different parameter. What is it? What are the parameters? So if I choose g1, what can I say about the empirical risk? So what is g1 doing? Effectively, if I take g equal to g1 over here, it's counting the number of times it is not equal to plus 1. Right? So basically the number of times yi is not equal to plus 1, or the number of times yi equal to minus 1. So this is going to be binomial n 1 minus alpha if g equals g1. And what happens if g equals g minus 1? Even in this case it is binomial, but what are the parameters? N alpha. Correct? So if I fix a particular g, then this is indeed a sum of ID random variables. But now what happens if I take the minimum over g in g1 g minus 1 of summation I equal to 1 to n indicator g of xi not equal to yi? What does this look like? What would be the g that you would choose? Correct. So depending on the yi's, how would you choose g? Correct. Correct. So if there are more ones, you basically choose g1. Correct. Well, not necessarily. So it depends on the realization of the yi's, right? So depending on the realization of the sequence y1 through yn, if there are more ones, then you choose g1, and if there are more minus ones, then you choose g minus 1. Correct? So in any case, this risk, of course, it's sort of I've removed the scaling 1 over n, but this particular risk cannot exceed n by 2. Do you agree? It can never exceed n by 2. So this is basically equal to the minimum over the number of ones and the number of minus ones. Correct? But this is not a sum of IID random variables. So, and even so you, just for this very simple example, this is not a sum of IID random variables, some complicated function. In general, the class G could be finite, it could be countable, it could be uncountable. Right? So effectively, you should think of the empirical risk, the minimum empirical risk, as basically some kind of a minimum of a random process. Right? For each G, you have a random variable which corresponds to the empirical risk for that particular classifier, and you're taking the minimum of this overall possible classifiers in your set. So for example, if let's say that G can be parameterized by a real number, then you can think of Rn of G as basically a random process indexed by the reals, and you're asking for the minimum of this particular random process along this. What is the infimum of this particular random process? Right? That's the right way to think about this. So for each realization of x1, y1 up to xn, yn, you get a different G and a different empirical risk. Okay, so this is slightly harder to analyze. So before we proceed, let's look at the different quantities that we've defined and what we are really interested in. Right? So for a given G, recall that Rn of G is basically the empirical risk of a given classifier. Right, and we defined Gn to be the one that minimized the empirical risk. Correct? So for a given G, Rn of G is a sum of IID random variables. Gn is also a random function which depends on the realization of xn and yn. There's also a G star, which you can think of as the one that minimizes the Bayesian risk So this is expected value of, or in other words, the one that minimizes the probability of error among this entire class of functions that we choose our classifier from. And corresponding to this, there are two kinds of risks. One is R of G star, which is basically just this particular quantity, the minimum overall G in G of probability that G of X is not equal to Y. And you can also think of Rn of G star, which is again a random variable. If I choose this particular G star, then what is the empirical risk that this can achieve? Okay. And there's also an R star, which is the optimum Bayesian risk, right? Which is essentially arg min over all possible G probability G of X is not equal to Y. Right? Now, again, we're all running. The difficulty that we have is that we don't know this joint distribution. We don't know the right class of functions from which to choose in order to ensure that we get the minimum risk. So we restrict ourselves to a class. Right? For again, there are multiple reasons why you would want to restrict yourself to a particular class. For example, to avoid overfitting and so on. But we'll restrict ourselves to some subset of functions. And again, here we don't have the joint distribution, but instead we're working with samples. Right? So the question is, if I perform empirical risk minimization, then how close am I to R star or even R of G star? So Rn of Gn, so ultimately what can we observe? Our observables are samples xn and yn. From this I can compute Gn and I can compute Rn of Gn. Right? So suppose I did this, I chose one particular classifier using empirical risk minimization. Now if I observe a new sample, how do you think I could quantify how well the classifier performs? Essentially, how well it performs on a test sample. Correct. So R of Gn would basically give me the performance on a new test sample. This is basically the probability that Gn of x is not equal to y. That is simply R of Gn. Correct? So really the quantity that we're interested in is R of Gn. Right? Our ultimate goal is always to design a G that minimizes R of G. Not just Rn of G. We're just using Rn of G as a proxy for R of G. So obviously it makes sense to look at how close Rn of, after all we're trying to find, we know that Rn of Gn is small, but we want to know how close this is to R of Gn. So hopefully this quantity is small. But ultimately our goal is of course to find out how close is R of G to how close is R of Gn to R of G star, right? Because this is the best in the class. So G star is the one that achieves the least test error among all possible classifiers in my class. Right, so our goal is to somehow get bounds on this particular quantity. Now, if we were able to show that R of Gn is close to Rn of Gn and R of G star is close to Rn of G star, then there's some, right? So the goal is show that R of Gn minus R of G star is small, right? Or in other words, try to find out what is that n. So what is the minimum number of samples required to ensure that R of Gn is very close to R of G star with high probability. But what do we know so far? We know that for a given G, so we know the following. For a fixed G, the probability that Rn of G minus R of G is greater than some epsilon is less than or equal to e to the minus n epsilon square times some constant. This is what we have. But we have no way of knowing what is the best, what happens to Gn, because Gn itself is a function of the samples, right? But suppose I'm able to show that for all G, Rn of G is close to R of G. Then that automatically gives me a bound on R of Gn minus Rn of Gn. So in other words, if I can show, or if I try to find the probability that R of G, so let me try to put it in a slightly different way. So ultimately I want a bound on R of G, right, for a given G. So for any G, I can write R of G to be equal to Rn of G plus R of G minus Rn of G. Done nothing here. But this is less than or equal to Rn of G plus the maximum value of this particular one over all possible G. Right? Sorry? The maximum will be 1. The maximum will be 1, but I want to show that it is significantly smaller than 1. Yeah, that's the goal. Right? Because I know that R of G is anyway less than or equal to 1, so that's not particularly helpful. But what I effectively want to show is that this quantity is really, really small. So in other words, I want to know what is the probability that R of G is less than or equal to Rn of G plus some epsilon. That amounts to saying that what is the probability that R of G minus Rn of G is less than or equal to epsilon for all G in G.
What we know for a particular G.
For a particular G.
There exists the G.
No. For a given G, if you fix a particular G, and I only take, I just allow x1 through xn to be independently generated, then this quantity is less than or equal to epsilon with probability 1 minus e to the minus n c square epsilon square.
To show that for the same samples.
Correct. So
for multiple G's.
Correct.
For any G.
For any G.
You are exponentially.
Correct. So suppose that the number of the class of functions G, it is finite. Then can we do something? Can we get a handle on this? So I want to show, or I want to find what is the probability that the supremum over all G in G, R of G minus Rn of G is greater than epsilon. Assume that the class is finite. What's the standard trick that we've been using so far? We can just use the union. Okay. So we know that for a given G, this quantity is less than or equal to e to the minus n times delta square. So this is less than or equal to the summation overall G in G probability R of G minus Rn of G is greater than epsilon. This is a quantity that we know very well how to handle. So this is less than or equal to the size of G times e to the minus n times some constant times epsilon square. Okay, so this is great if as long as we have a finite class, we can get a bound on this particular quantity. We know that the test error is going to be close to the training error with high probability. And we can find the smallest n for which this quantity is less than or equal to some delta. Right? But now what happens if this class is infinite? I can't use this union bound anymore. Right? So before that, let's quickly recall. So here's theorem. So if the class is finite, then we have the following bound: the probability R of G is greater than or equal to Rn of G plus, again, I'm not optimized over the constants, but what you can show is that probability that this is greater than this plus 2 times log size of G plus log 2 by delta divided by 2n is less than or equal to delta. Right, so if as long as so the amount of error that I incur, so these are two different ways of looking at the same quantity. If I fix a target error, then this is basically the epsilon that I can choose. This is the epsilon that I would get. Right? And one can also show, I will not prove this, but you can show that the probability that Rn of G is greater than R of G star plus something similar. Basically, the constants might be a little bit different. Log size of G plus log 2 by delta divided by 2n is less than or equal to delta. So this requires a little more effort because you also have to connect R of G star and R of G, but effectively it uses very similar techniques because you know that because we have this particular quantity, the supremum of this difference is greater than, this is going to be very close, right? And because Gn is essentially achieved by minimizing the empirical risk, and you know that the empirical risk is going to be close to the true risk for all functions in the class. The one that minimizes the empirical risk is also going to be close to the best, close to the best estimator with high probability. right? Because we have this uniform bound on all functions G. So essentially we get the other almost for free. So the best estimator from the class. From the class, yes. That's the only point we're trying. Right? Because after all, the class, if your class is not rich enough, if your class is not good enough, then you could be far away from the base optimal list. But within your class, you know how well you're going to do. If you do empirical risk minimization, you're going to be very close to the best estimator in your class. And you have a bound on exactly how many samples you need to ensure that you're within a probability. So with probability at least 1 minus delta, you're within an epsilon of the best, the minimum risk that can be achieved within this class. Right? But again, all this only works for finite classes. Right? What if the class is infinite, or if the, and of course you see that this grows with the size of the class. Right? But this in fact, these bounds are not tight, right? Because it could be that you have a very large class, we're using a very loose bound, which is the union bound, and that's definitely not very good. Of course, we're dealing with a handicap, that is we are given absolutely no information about the true probability distribution. We don't even know if G has any particular structure that we can exploit. This is for an arbitrary class of functions G and an arbitrary distribution Pxy, and we're just told that we have to do binary classification. That's it. But this is still a surprising result, showing that something can be done. But of course, what if G is infinite, countably or uncountably infinite? Does it mean that there is no hope to bound this at all? Of course, the union bound is now weak. I can't use the union bound any longer. So how do we improve? Right? So for this, let's look at the loss, right? The empirical risk. So the empirical risk is a sum of Bernoulli random variables, correct? So let us look at the following quantity, xn, yn. I'll define this set as basically the class of all possible individual losses that can occur. Okay, so for given n samples, this is, let me put it the following way. So for a given G and for a given xi, yi, let's just call this this is just the indicator random variable, that G of xi is not equal to yi. Okay, and I define f xn yn for a given realization of xn yn. This is equal to all possible configurations of this eta function, basically the errors. All right, so this is, so for a given G, this can take, so this is eta G of x1 y1 up to eta G of x2 y2 for G. Sorry, x and y. X and y in.
You would want to find the G belongs to the class.
Yes.
The sum of the
That
will go back to
will go back to that, but effectively the random variables that ultimately influence the empirical risk are these random variables, right? So this is a function of G. It's also a function of X and Y n.
So you want to go back to the equality.
Correct. Ultimately, I somehow want to be able to use the Efron-Stein inequality. And the point here is that even if the class of G's is infinite, for a given X and Y n, the empirical risk cannot take widely different values. Right? In fact, this configuration itself, what is the maximum number of values that this configuration can take? 2 to the power n values, right? So the size of f xn yn is 2 to the power n. So this is bounded, which is fine. I mean, it is finite, but we're kind of interested in classes for which this quantity is not too large, right? It's not close to 2 to the power n, but something a bit smaller than 2 to the power n, right? So I'll define for a given class G, I'll define this SG of xn yn. This is called so for a given class G, I define the so-called growth function Sg as the maximum of f of xn yn over all possible xn and y.
Maximizing over the mistake.
You're maximizing over so here in some sense there are two sets of maximizing. Okay, so this for a given xn and yn, this is basically a set, right? How many different values of the configurations can I get among all possible G for a given realization of samples for a given data set? At most 2 to the power n. Potentially it could be fewer than that. In particular, if let's say that G is small, the size of G is small, suppose that G just takes 2 values. So really there are only 2 values. For any n, there are only 2 different values that this can take. Correct? So even if G is an infinite class, it's possible that there's not a lot of variation, right? Because in fact, if I choose the class to be too rich, then you really cannot hope to have any form of uniform convergence. Basically, what I want is that for all functions G, the empirical risk should converge to the expected risk. Okay, that's the kind of result that I'm aiming for. And if G is too rich, then it's not possible to even expect that. So I need to constrain this class of functions in some manner. And one way is to constrain that is to say that this quantity does not grow too fast. So this is at most 2 to the power n, but hopefully it is something much smaller than 2 to the power n for n large n. You're maximizing over all possible samples, all possible realizations. Yes, all possible realizations. Okay. Again, the reason it seems like a very, very loose bound, right? And the reason why we are forced to use these loose bounds is because we're given absolutely nothing about the true distribution. If we knew something about the distribution, we could have done something much better. But we want this to work irrespective of what the true distribution is. Right? So the claim is that if the growth function is, if this quantity is not too large, then we can have a good bound on how well the empirical risk minimization algorithm performs. The claim is that
G as an input.
yes, so takes the class as input and spits out one particular. So in other words, the growth function tells you how rich the class is or how diverse this class is. Right? So if n is sufficiently large and G is finite, then SG would just end up being the size of G.
SG is the function of small g.
So we're looking at the size of the class, right? If the size of the class is finite and n is large enough, then SG would end up just being the size of the class, because you can have only so many configurations. You can't have more than those many configurations.
More like growth number.
It's a growth number, correct? Yeah, that's right. So it's a growth number, and hopefully beyond a certain point, it doesn't grow much. So for example, in this case, beyond a certain n, if G were finite, beyond a certain n, this growth function, it basically stops growing. It's fixed. And that's sort of the regime that we're interested in. So we have the following very famous result in binary classification, which says that the probability that R of G is greater than Rn of G plus something similar as we had earlier, the error function 2 times log Sg of 2n plus log 2 over delta divided by n for any G. Again, this is a uniform bound, uniformly over all possible G in the class. This is less than or equal to delta. So we have a similar bound as before, but this works for potentially even infinite classes. But if your class is too diverse, then there's nothing much you can do, because if suppose that this were growing, say linearly with n, right? So for example, if we know that Sg is at most 2 to the power n, right? So this would log 2 to the power n or 2 to the power 2n would be some constant times n. So the error would be bounded by some constant independent of n. So that's not particularly helpful, right? And that is kind of intuitive, because we cannot have uniform convergence if our class of functions is too diverse. Right? So again, I'm not going to prove this particular result. It involves a lot more, but effectively it uses the Efronstein inequality and the McDermott's inequality defined on this quantity f, x and yn. And you can see why that is the case. If I take a particular, if I change the value of one xi yi, one particular sample, then this function f cannot change much, right? And you try to use that. There are some more concepts that again we don't have time to discuss, but you can look up the references that are there in the web page. There's a link to a paper called Introduction to Statistical Learning Theory. Which is a good reference. It basically outlines this and a lot more. There's also a paper by Wapnick, which I think has a similar title. And yeah, a number of other references. Any book on statistical learning theory would give you this theory. Right? So I think this is a good point to end. We saw a few tools used to, few concentration inequalities, but again, we've only just scratched the surface. There's a lot more that you can do. Our focus essentially was just on IID random variables, but you can generalize this to a broader class of functions or random variables that are dependent and so on. And that is really where the power lies. Even here, we only saw a few applications, but with just these results, you can derive many powerful results in coding theory, information theory, machine learning, and so on. Right? So, in fact, the textbooks that are put up on the web page, they have a number of applications. So, I do encourage you to go through those because it will give you a much broader overview of this field. Okay, so, let's stop here. Any questions? Okay, so next class we'll have a quiz. It will be the final quiz. There won't be any more homeworks. But yeah, so the quiz will basically involve everything that was covered up to now.